It's one thing to check the weather forecast for your city, but imagine trying to get a reliable weather report for a world 20 light years away.
It sounds like science fiction, but that is exactly what the James Webb Space Telescope has just done.
And today we are doing a deep dive into this exact achievement. We're talking about the atmosphere of an object called SIMP0136.
Right, and this object is basically the perfect laboratory. Webb gave us a full atmospheric forecast for it, and, well, the findings are much stranger than anything in our own solar system.
Okay, so let's clarify what SIMP0136 actually is. It's not a planet in the usual sense, orbiting a star, but it's not a star either.
Exactly. It's classified as a brown dwarf, which some people call a failed star.
Real star?
Yeah, it's about 13 times the mass of Jupiter, so it's huge, but it never got quite massive enough to ignite hydrogen fusion, and the key thing is it's just drifting through space on its own.
And it spins really, really fast, right?
Incredibly fast. A full day on this world is only about 2.5 hours long.
So being a rogue world is actually a good thing for us, because there's no blinding starlight getting in the way.
It's the perfect setup. It lets us see its atmosphere with amazing clarity.
But how do you even do that? How do you create a weather report from 20 light years away?
It's a technique called time series spectroscopy. So as SIMP0136 spins, Webb is just staring at it, capturing these tiny, tiny changes in its infrared light.
So it's kind of like watching a distant light bulb flicker.
That's a great way to think about it. And by analyzing those flickers, we can map out what's happening. We can see temperature, the chemicals in the air, and even the cloud coverage as different parts of it rotate into view.
Turning those faint flickers into a whole global model? I mean, that must require some seriously sophisticated tools and, powerful software.
Oh, absolutely. You can't just sketch this out on a whiteboard.
And that need for complex, powerful solutions actually brings us to our sponsor.
It's a perfect fit.
This deep dive is brought to you by Silk. If you need help uncovering where agents could make the most impact for your business or personal life, whether for AI training, automation, software development, you name it, Silk has the advanced solutions to handle that complexity. Check them out at embersilk.com for your AI needs.
So getting back to that forecast, what Webb found is that the atmosphere is layered. There are at least 3 distinct layers.
Okay, and what's in those layers? Not water clouds, I'm guessing?
Not even close. We're talking about clouds made of sand-like silicate grains, iron, and even bits of rock like forsterite.
Clouds of molten sand and rock. It really does force you to redefine what weather can even mean.
And there was a surprise in how they behave. The old models assumed the brightness changed because of patchy, flickering clouds.
But that wasn't it.
No. The data showed the silicate clouds are actually pretty stable and uniform. The variation was coming from somewhere else.
So if it's not the clouds, what was the big dramatic discovery here?
It's what they're calling the aurora heat engine. The upper atmosphere is about 300 degrees Celsius. That's 570 Fahrenheit hotter than it should be.
Wow. And that heat is coming from auroras? But wait, there's no sun, no stellar wind to power them. How is that possible?
That's the incredible part. The auroras on SIMP0136 are driven entirely by its own internal processes. It has a super strong magnetic field that creates these massive supercharged auroras all on its own.
So it's a self-powered light show.
A light show that acts like a heat engine, pumping enormous amounts of energy into the air without any help from a star.
That's a huge finding. And what about deeper down? Did you see weather there too?
We did. We detected these subtle temperature swings, only about 5 degrees Celsius, but in the deeper layers.
And that means?
That's the signature of massive turbulent storm systems. We could be talking about storms that rival Jupiter's Great Red Spot.
So stepping back, why focus all this energy on a single brown dwarf? What's the bigger picture?
Well, SIMP0136 is crucial practice. Brown dwarfs are great stand-ins for the giant gas planets that we see orbiting really bright stars.
Right, the ones where the star's glare makes it impossible to see the planet's atmosphere.
Exactly. So all the techniques we're perfecting here, the precise measurements, the climate modeling, these are the foundational steps. This is how we'll eventually be able to forecast the weather on smaller, maybe even Earth-like exoplanets.
So we're essentially building the toolkit for understanding the climate on any world, anywhere.
We are. This proves that complex, dynamic weather can exist even on these lonely worlds without suns, just driven by the planet itself. It's a really inspiring leap forward.
A forecast of rock clouds, giant storms, and self-powered auroras. I love it. If you enjoy this deep dive, please subscribe to this show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.